Okay, folks, let's get after it in the second of two example problems in our exploration of applications of differential equations. Okay, so being the math geek that I am, I wanted to determine the temperature model for the coffee in my $30 Yeti tumbler. Actually, that's a little bit incorrect. It was 35 because I got it monogrammed with my initials, JB. And here's what I know about coffee. It cools at a rate proportional to the difference between its temperature and the ambient temperature. For those of you who don't know what ambient temperature means, that's room temperature. The coffee's initial temperature is 170 degrees Fahrenheit, and the temperature in my house is a nice brisk 68 degrees Fahrenheit. After a half hour, I measured the temperature of my coffee. It was 145 degrees. So let's go ahead and just capture a couple things here that were given in this problem. We have an initial temperature at T equals 0 of 170 degrees Fahrenheit. So that's, we might call that like initial condition number 1. We have ambient temperature, 68 degrees Fahrenheit. And we have another condition here. I won't call it an initial condition, but another condition. I'll just call it number 2. And that is after a half hour, so we'll say 30 minutes, coffee is 145 degrees Fahrenheit. So that's what we know from the problem. And then the highlighted piece cools at a rate proportional to the difference between its temperature, T, and the ambient temperature, A. So we have to write a differential equation that models the solution. I'd like you to check your answer with me before moving on. So right now I want you to go back and reread that highlighted portion and see if you can come up with the differential equation. Seriously, would you please just try to do it on your own instead of just fast forwarding it until I do it? Okay, now I'm going to do it. Okay, so it cools. So we're talking about a rate. We'll call that rate T prime, T, big T for temperature. It cools at a rate proportional, so I have a proportionality constant, to the difference between the temperature of the coffee and the ambient temperature. So it jumps right off the page at me when I read that highlighted thing. Cool at a rate proportional to the difference between its temperature, T, and the ambient temperature, T sub A. It may not jump right off the page at you, but I hope it will in a few short minutes. Another way we might want to write this is dt, and that's confusing. That's the rate of change of the temperature, big T, with respect to time, little t, is going to be equal to that same proportionality constant times T minus T sub A, where T, big T, is the temperature at time, little t. Okay, let's go ahead and find the general solution to this differential equation. And we know what our 4-step process is here. We're going to separate, and then we're going to integrate. And then we're going to work at rewriting this bad boy. All right, folks, real quick here, commentary. We have seen this before. And we know that we can split that up because when two exponents are added, that can be rewritten as a product of two quantities in the same base. I think you know what I'm going to do here. I'm going to change this to C sub 1 throughout the problem. And then I'm going to call this a new constant that's just plain old C. So what we have here now is the following. I have e raised to the ln of the absolute value of t minus t sub a. I can rewrite that as the absolute value of t minus t sub a. Right hand side is going to be c times e to the kt. Let's take a minute to talk about the absolute value of t minus t sub a. We have really two different conditions. If t minus t sub a is greater than 0, then c will be greater than 0. But if t minus t sub a is less than 0, C will be less than 0. So I'm now taking care of what would be a piecewise definition for that absolute value function. Because I've showed that I can take care of both the positive values of t minus t sub a and the negative values of t minus t sub a, I can take care of that with the constant c. The next step, I am not going to write the absolute value symbols. It's just going to be t minus t sub a equals c times e to the kt. Now we're almost done. Let's just solve for t by adding t sub a to both sides. And there you have it. That is the general solution for the differential equation that we had up here. Okay, let's now move on to part B. Part B says find the particular solution that models the data collected by Mr. Vass. We're now going to sub in that initial condition, which was a temperature of 0, or excuse me, a time of 0 and a temperature of 170 degrees Fahrenheit. Ambient temperature, 68 degrees. C times e to the e raised to the k times 0. K times 0 is 0, so this constant, this value here becomes 1. So then we have the following. 170 equals c plus 68. A little simple arithmetic gives us a value of c equals 102. Okay, now we have one, we still have to find that constant k. In order to do that, we're going to plug in that other condition, which we said after 30 minutes, the temperature of the coffee was 145 degrees. So this one takes a little more work than the previous one. The first thing I'm going to do is I'm going to subtract 68 from both sides. Second thing I'm going to do is divide both sides by 102. Next thing I'll do is take the natural logarithm of both sides. And the natural log of e to the 30k is just 30k. I hope that I don't have to walk you through the logarithm properties to show that, because we've done it several times. Now to solve for k, we're just going to divide both sides by 30. So k is this beautiful constant here, ln of 77 over 102 divided by 30. That's our constant k. It's not pretty, I'll be honest with you, but it is exact. So now we're ready to write the particular solution. Let's go ahead now and write our particular solution. And folks, it is not an easy one. It's going to take us a little bit of space here. The temperature at time t is equal to the constant c, 102, times e to the k, that's our friend ln of 77 over 102, all divided by 30 times t, plus ambient temperature, 68 degrees. There it is, folks, in all its glory. You can use that equation right there to find the temperature of my coffee at any time t. Let's go ahead and do one other thing here. Let's make sure we know that this entire quantity is in the exponent on e. I know that when those exponents get kind of large like that, it sometimes can be confusing. If you want, for simplicity, you can convert that ln of 77 over 102 all divided by 30. You can convert that to a decimal. Just make sure you keep enough decimals there so you don't affect the precision of your final answer. Okay, now we got a little bit of an extension here. It says, how long will it take the coffee to cool within a degree of the room's temperature? So let's break this one down. So we're first asked how long. That means we need to find a time t. And we are cooling to within a degree of the room's temperature. And the room's temperature is, the ambient temperature is 68. So we're really here, we need to find out how long to cool to 69 degrees. That's really what we're doing here. So let's go ahead and plug in what we knew to our temperature equation. We're interested in a temperature of 69 degrees. We have 102 e to the ln of 77 over 102 divided by 30 times our unknown time plus ambient temperature of 68. Okay, so let's start here and let's subtract 68 from both sides. That gives us 1 equals 102 e to the ln of 77 over 102 divided by 30 times t. Let's divide both sides by 102 now. Okay, we've divided both sides by 102, and I avoided having to write out that long exponential piece again. Okay, so how do we get that t out of the exponent? Remember, everything here is up in the exponent on e. Well, I can take a natural log of both sides, and that'll give me something that looks like this. Okay, so now we're ready to solve for t. It's just a matter of doing a little bit of algebra here and trying to make sure that when you do this in your calculator to get an approximate answer at the end, you're careful with all the expressions that are inputs to these logarithmic functions. So we're going to get something that looks like this. When you grip it and rip it in your calculator, you're going to get this as an answer. It's about 493.5 minutes. For those of you who are interested, that's about 8.22 hours. It's quite a coffee mug. All right, folks, let's go ahead and finish this off. This problem is an example of a law by one of the godfathers of calculus. What is this law called? You know it, friends. Maybe you remember this one from pre-calculus, possibly even chemistry. This is Newton's law of cooling. Newton's law of cooling also works if the coffee were iced and was warming up to room temperature. Okay, so let's provide you here with a little bit of a summary. Newton's law of cooling. The differential equation T prime equals K times the difference between the temperature of the product and the ambient temperature has the general solution of the form T equals C times e to the KT plus ambient temperature. And that's it, folks, for Newton's law of cooling and this second example problem and applications. I hope you tune in for the brief video that I have to follow this with a couple hints on WebAssign.